All right, welcome back. So in 10.6 now we're going to be discussing what are called alternating series. An alternating series is a series where the terms keep switching from being positive to negative. In other words, they alternate. So now we already know, because we've investigated it a couple of different times now, that the harmonic series, which is 1 plus 1/2 plus 1/3 plus 1/4, and so on forever. We know, of course, that that diverges, and we were able to establish that with the integral test. So now we ask, what about the alternating harmonic series? What about the alternating harmonic series? What if we alternate the terms from positive to negative? Will that make a difference? In other words, looking at the series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus and so on forever. Well, we can write that in symbols as the sum as k goes from 1 to infinity of minus 1 to the k plus 1 over k. Okay. So we're using this alternating sign, which is either going to be a minus 1 to the k or a minus 1 to the k plus 1 typically. Generates an alternating series. So in this case, since we're using k plus 1, that means the odd terms in my sequence will always have a positive sign. The even terms will always have a negative sign. If we did it the other way, minus 1 to the k, then the even terms would get a plus sign and the odd terms would get a negative sign in front of them. That's what that minus 1 to the k plus 1 and minus 1 to the k does. So a reasonable question here is to ask, does this thing converge? Does it converge? You might be thinking, well, since the alternating one, or the original one doesn't, then surely it would complicate things more with alternating signs. It won't converge either. Well, let's consider some of our partial sums. Let's consider the first few terms. So, in particular, let's consider the first 6 partial sums. Okay, the first 6 partial sums. Okay, so S1 would, of course, just be 1. S2, we would bring in minus 1/2. So it'd be 1 minus 1/2. So S2 would be 1/2. And then we'd add 1/2 plus our next value, 1/3, which would jump us up to 5 over 6. And we keep going. S4, we would subtract 1/4 off of 5/6. And you can confirm that that'll be 7 over 12. 7 over 12. And then S5, we're going to add on 1/5 to that. And it'll actually get us to 47 over 60. And then subtract off 1/6 from that. And our 6th partial sum is 37 over 60. So unfortunately, when we look at these all together, we look at each of these all together. We look at these all together. When we look at these all together, things are just bouncing all over the place. 1, 1/2, and 5/6, and 7/12, right? And it just keeps bouncing around. Things look, I don't know, not very good. But if we look at things from a slightly different perspective, then we can actually make a little bit of progress. Okay. So look at the odd sums. 1, 5/6, 47/60. And let's look at the even sums. 1/2, 7/12, 37/60. Okay. What do we observe? Well, the odd sums, 1, 5/6, 47/60, and so on. These numbers are always getting smaller, right? This is always decreasing, right? It's always decreasing, right? And you can see this because after the first term, right, when you get to your third term, it's 1/2 plus 1/3, which is smaller than, 1/3's smaller than 1/2. So we're always going to be taking it down just a little bit when we get to the next term. And the same thing, 1/4 is bigger than 1/5, so -1/4 plus 1/5 is always going to be adding on a small amount. So when we look at the odd terms, this is always going to be decreasing. Now, since it's always going to be decreasing here, right, this thing is just going to keep going down, 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 getting smaller. Now, we're always taking off a little bit more each time, a little bit more each time, okay? So this thing, though, is bounded from above by 1, right? And it's actually bounded from below by 0. So this thing here is always decreasing, and it's bounded. So we had a result, which was kind of a theoretical result, but it's actually important here. Sequence, sorry, 10.2, right? It's an important idea here. And that is that every bounded monotone sequence converges. And so this sequence of the partial sums, the odd sums, right, it's always decreasing. It's always decreasing, right? And so it's also bounded, right? Right? The absolute value of my terms is never bigger than 1, right? It's always going to be bounded. And so that's decreasing. And so therefore that series is going to converge. When we look at the even sums, what do we see? Well, we see 1/2, then we see 7/12, then we see 37/60. Right? Every one of these is getting bigger. 1/2 is 30/60. 7/12 is 35/60. Now it's up to 37/60. Right? These things keep increasing. And that pattern is going to continue because if you go back to the terms, every time you get to the next even sum, well, you've added on a 1/3 plus minus 1/4. 1/3 is bigger than 1/4, so you've added on an amount to it. Then you're going to add on a 1/5 minus 1/6. 1/5 is bigger than 1/6. So you're going to add another point, and then a 1/7 minus 1/8 will get added on for the next one, and so on. So this thing is always increasing. Is always increasing. Now it's bounded from above because by 1. Actually, it's actually bounded from above by 1. And at the very least, it's definitely bounded from above by 2. So this thing's increasing. So this sequence is going to converge. Right? And of course, they have to converge to the same thing. So therefore, the alternating harmonic series will converge. Okay, the alternating harmonic series will converge. Okay, so that's our result there, that the alternating series alternating harmonic series will converge. Okay. even though the harmonic series itself will not converge. Even though the harmonic series itself will not converge, turns out the alternating harmonic series does converge. And then a really good question is, well, what does it converge to?